Hi everyone, welcome to the Natural Language Processing course. Funny, right? I want to see you here. Today's class will talk about language models, finally. Now that we have the basic idea how to represent words, how to move from a word, let's say text representation, to a numeric vector, the idea is for us to start using this knowledge to kind of represent language. And how we do this? Through language modeling. First, we'll talk about statistical language modeling, of course. Then we'll talk a bit about anagrams, bunny version of evaluation, and then we will revisit the smoothing that we're talking on the previous lecture, how to deal, for example, with those zero or sparse representation. Okay? So, probabilistic language model. Does anyone here have an idea what a language model is? Okay. Oh, good. So pretty much a language model is a probabilistic representation of natural language. So how do we approximate, let's say, the occurrences of word given a specific time frame in the past, and we use this to represent that language. So theoretically, the more text you have, the better you can represent the language. And then we talk about language modeling. We're pretty much talking about two things. One, the model can be predictive, in which we use this model to predict the next words based on previously seen words and how far you can look. That's debatable, depending on the approach that you're using. In a theoretical model, you should be able to look as far as you want. In practice, it's not that feasible because of some limitations. Or explicative, in which we compute the likelihood of a given sequence. So given a sentence, we want to see how probable it is for this to happen. And moving a bit on more practical applications. So the idea is we use this language representation, this model, to, let's say, calculate that a given sentence makes more sense than some others. So let's say if you're having a speech recognition system and you're not sure which sentence was captured by that, which sentence makes more sense, which sentence is more probable? The probability of I saw a van or eyes of an ant. So most likely the first one. Or handwriting recognition, it was fast is most likely to be correct than it was fast. Spelling correction, if you change, let's say, A for a S or a S or D and so on. So the idea is to use this knowledge that we have after looking so many words, and then we can apply this to calculate, for example, in spelling correction, about 15 minutes from is most likely occurred, and about 15 minutes from. Also, machine translation systems, optical character recognition, text suggestion, and so on. Pretty much anything that we can calculate a given probability for a sentence, we can use a language model to see if that makes sense or not. Okay? And how that look for us? The main task is to compute the probability of a sequence or a sequence of words. So in this case right here, we want to know what is the probability of a given sequence. So the probability of all the words occur in a given order right here. And then also another related task, we want to calculate the probability of a given word given a specific span that we have. So if you're either calculating what is the next word or what is the probability of an entire sequence right here, we're talking about language model, right? And this is pretty much the idea that will also apply in neural language model. It's exactly the same thing, but then you code this in a bit different and you adjust, let's say, parameters a bit different, okay? But it's pretty much the same idea. And how can we calculate this? So the idea is the probability of each next word is related to its word frequency, of course, and then to calculate the likelihood of a sentence, we can simply calculate the probability of every single word and multiply by them, right? This if you have, let's say, a toy example, it might fly by itself, but there are problems with this representation, right? For example, let's say the probability of all those words are really, really small if you consider, I don't know, the English vocabulary, for instance. So if you multiply those numbers, most likely you're going to have an underflow or something like that, right? Also, the other way around, if you don't have enough examples, your probability might not be that accurate depending on the problem that you're handling. So another way to deal with that, instead of considering that all the words, they are independent, we consider that the words are related somehow. So remember the previous class, I think, when we were talking about the sequence San Francisco? If you have Francisco, if you're deciding what is the next word after San, most likely will be Francisco, of course, in a very controlled environment. But if you rely on the previous words, most likely it will be more realistic, because this is how we speak, right? Let's say we don't simply say, hello, tomato, computer. So that doesn't make any sense, but I don't know, in the entire vocabulary, probably those words, they have a high probability to occur, but we have a specific order. In the same way we have this specific order and concatenation of words, we can also explore this in our systems and just looking back to see what is the next word, all right? So the first idea that we have, which we thought was smart, is pretty much the unigram model, in which we take a look on every single word independently, and then the far, or let's say, the co-occurrence of words that you're taking into account, we call this an anagram. So a bigram, you're considering 2 words, a trigram 3, and so on and so forth, all right? So, for example, the relative word frequencies are better than the equal probability of all words. Of course, if we have a corpus with 10,000 word types, so unique words there, we can pretty much say that the probability of every given word, it's 1 over 10,000, right? But that doesn't match exactly what happens in reality. So what we want to do is we want to explore the conditional probability simply because this is closer to reality. So if we have here that dog in a given corpus might be a rare word. However, if you have a previous word as embarking here, dog makes way more sense, right? And this, of course, it boosts the probability of having the word dog right here. So just to give you one idea, if we consider letters sequences are independent of each other and we try to build a language model on top of that, we would have some gibberish like this. So imagine that every word has equal probability. So as we are predicting the next word, we have X and then F, O, and so on, and we have this gibberish right here. Now, if we are considering the frequency of words in the English text of the vocabulary, we see that it's not exactly make much sense, but you see that we are getting there. At least we have some attempts here, okro or EU and so on. Now, the further we move to that, if we have a second order approximation, we see that we are already able to see some words like on, are, and I think that's it for this example, Andy to some extension. And the more you grow with that, the more, let's say, the more sense your text will make. Can you already see a problem in going this direction? Because independent, yeah, okay, doesn't work. 2, 3, yep. A lot of what? Exactly, and also how far you have to look back. I mean, infinite, right? And this problem, by the way, is still persists today with some more modern approaches. And there are some tasks that are still affected by this. For example, if you're working with text generation, which is essentially language modeling, but you want to create a paragraph, yes. Now we see that's getting there. It's pretty decent. But let's say you have to write a book completely, from beginning to end, not by parts. when we're reading something, sometimes we relate things from the last page to the first one, a character or something. So if you're using this kind of models to generate a text without any interruption, you see these models, they start to hallucinate quite easily, and it's harder and harder to make this correlation between, let's say, the distance between those, let's say, the sequence. Okay? So, how we compute the probability of its water is so transparent that. So as we saw before, we want to compute the entire probability that we have right here for the sequence, so all the words there. So we should simply calculate, we multiply the probability of every single word. We already saw that that's not how we do it. Instead, we're going to use the chain rule of probability to deal with that in a way that we'll look to the previous states that we have, and then we can have a better representation of that sequence. So if I want to calculate what is the probability of the sequence from A to D, it's pretty much the probability of A by itself, and then what is the probability of B, C, D, given that I have A. And if we expand this to all the other possible co-occurrences, and we just take the inverse of this fellow right here in this line, we have that the probability of the entire sequence is, you start with the first word or token in that sequence, and then you use that occurrence to condition to the new probability that you have to calculate, and you do this until you finish your sequence. More mathematically, you're just pretty much multiplying every single conditional probability that you have. So the sequence of previously seen words, they're getting bigger in this case. So for our example, if I want to calculate the probability of its water is so transparent, I first do its, and then what is the probability of water given its is given its water, so its water is transparent, and so on. All right? Needless to say, this is quite problematic, because if you're doing the probability distribution or the language modeling for one single sentence, it's rather easy. But what happens if you have to do this for an entire book? In a theoretical model, yes, it's possible. But in practice, this doesn't work, simply because we have too many possible sentences, and then for you to have a probability, let's say, representation of a specific sentence, the longer it gets, it's hard to find that and have a, let's say, a truthful probability for that. So most likely you will have a probability for it's water or so transparent, that, but then the moment that we have a larger sequence right here, we won't be able to do this, and then the last thing we want is to divide by 0, right? So this here doesn't work for us. Needless to say, we'll never see enough data for estimating those. So it doesn't matter if you consider all the knowledge, if you consider just the tokens that we have in, let's say, in human language, you have so many different combinations that you won't be able to have a probability for every single sequence of them, all right? But the good thing is we don't have to worry about this, and if you were here in the very first lecture, I mentioned this. So we can use the Markov assumption for that, in which a stochastic process has the Markov property if the conditional probability distribution of future states of the process, conditional on both past and present states, depend only upon the present state, not on the sequence of events that preceded. A process with this property is called a Markovian process. In short, you don't need to look for the entire sequence. Just look a bit in the past and you're good to go. And that's quite useful for us. And why that? Because when we have the entire sequence, let's say we're trying to predict the probability of given the sequence that we just saw, it's water so transparent that we don't need to consider the entire thing. If I just take a peek look what was behind, like what is the probability of given that, it's pretty much the same thing as the entire sequence. Or if you want to be a bit better, you increase your context in this direction. Okay? But again, how far you play with your context, it depends. You'll see that this kind of problem, it persists on more recent approaches as well. Yeah, this is just the mathematical representation that instead of looking to the entire sequence, we'll just look to a given, let's say, snippet of that sequence. All right? And how we can explore anagrams and language models. We'll talk also a bit more about this. You'll be surprised how a simple anagram can fool you. Later on, we'll show a test. I want to see if you can distinguish a text between an anagram probabilistic model from a real text, right? So, get some water. What is a unigram model? And a unigram model is pretty much the simplest case in which we calculate the probability of every word separate here. So this is just, I don't remember exactly what is the corpus it was trained, maybe the English corpus. But so if you're just using, instead of the characters as the example we saw before, which is really hard to predict or to make sense of that probability, here we're talking about entire words. So fifth and of futures, all of this here are generated by using a unigram model, so considering one word at a time. On the bigram model, we see that things start to form a bit more, a bit better, in which we consider not only the word itself, but the previous word. Right? And of course, I didn't mention, but we can grow this to trigrams, 4grams, 5grams, and so on and so forth. A good way to use anagram models, especially if you're more on statistical approaches, let's say you have a text and you want to see entities that have a compound name or words that should be glued together, and was the boy sitting in the front row, he asked this last class. How do I know that two words, they belong together? You can use a bigram model or a trigram model to see which of those words they have a high probability given a corpus. And then for those anagrams that have a high probability, you will keep. Those that do not have a high probability, you simply discard, and then you use this, let's say, enhanced text representation for whatever tasks you have later on. Okay? And how we do this, how we estimate this probability, think as we'll pretty much count the co-occurrences of these words divided by the previous word that we have in this case. So what is the probability of word I right here given its immediate previous word? We'll do the count of how many times those two words co-occurred. So the one that we're trying to predict in the previous one over the count of my history word, and for the sake of representation, we just use this notation right here. Okay? Another way to do this, also you can face this as a, let's say, the maximum likelihood here. So let's say you have any trials, case success, and a success probability of P for that specific word or characters, depending how you do this. You can understand this as an estimation problem. So if I can observe how many trials and success I have, maybe I can calculate the probability of that sequence of characters or that sequence of words. It's pretty much intuitive for us. If I know that a given pair occurs as many times and consider the entire vocabulary, it's pretty intuitive to just have the success rate of this, but we can actually show using this here how this would look like for us. So if we win a game, if we win 40 games out of 100, what is the maximum likelihood estimate of the probability of a game win? Intuitively, we know already it's 40%, right? So nothing new there. But if you want to actually make the calculation for that, we have the number of trials, the success rate, and we want to calculate the probability that will maximize this 40 games for us. And how we do this? We can simply take the first derivative and set to 0. And if we do the first derivative right here, 40 drops, minus 1 times everything there. And I won't go into the detail of this because this is not calculus. And then in the end, we'll have to obtain which p right here would maximize our probability. In this case, we know it's 0.4 because if we have either 0 or 1, this here will be equal to 0. Or you just take 40 divided by 100. This is just a short version of this. We don't need to waste time. And how we use this co-occurrence of words to calculate the probability of the co-occurrences here. So let's say we have these sequences, I am Sam and Sam I am and so on. By the way, it's quite normal when you're dealing with text representation to have some special tokens to delimit where exactly things start and when things end. It seems like a not very useful, let's say, artifact, but you'll be surprised how much this helped. Not only on statistical NLP, but also on neural language models. When we talk more about transformers, BERT, and so on, we'll see that we'll still rely on specific characters to say, okay, this sentence starts here, ends here, I break the sentence into 2 parts, and so on, okay? So in this case right here, what is the probability in this that any sentence starts with the word I right here? It's pretty much how many times those 2 here occur. So we have I preceded to the start of the sentence. This is the end of the sentence. 2 times, the first one and the last one, and we divide for how many times the previous token or the start token, the sentence started, so 3. And then we can calculate all the, let's say, the co-occurrence or the conditional probability of a given word given its immediate predecessor. Can you already see how that's a proxy for meaning? Because right now, yeah, this sounds really theoretical. I know account the co-occurrence, I know what's coming. Yeah. Can you try to extrapolate this, that if I know the previous state or the previous word, how that can embed some kind of semantic meaning for us? So when we are considering entire sequence, you see that by just looking how probable one sequence is, it might convey a meaning. For example, I know that every time I have a noun, it's preceded by an article. Or if I'm talking about food, it's most likely, I don't know, I'll also have types of food related with that sequence and so on. But we'll see how we can extrapolate this knowledge in a bit. There are some studies and some already calculated anagrams and language modeling. This, to be honest, this is a bit old, but it's still, as a historical fact, is still good. And then what we can do is, sorry, we should also mention this. These are some samples from the Berkeley Restaurant Project sentences, which is pretty neat. So you can come up with some sequences that are most likely to make sense. So like, can you tell me about any good Cantonese restaurants close by, or mid-price Thai food is what I'm looking for. And the cool thing is, when we have this kind of bigram right here, like Thai food, it's most likely to occur, and you know that this is about ethnicity food. You wouldn't have something like English food right here, which is pretty neat embedded knowledge, at least for me. So how do we work this in our text representation? So let's say we are considering the previous corpus as our vocabulary representation right here. So if I want to represent, if I want to see, I don't know, the co-occurrence of my words right here, I'll say that I and I, they co-occur 5 times. I want 827 times. And just by looking into this, I already know that some of the co-occurrence of word, they are not very important for whatever representation that we have. For example, if I have here like Chinese lunch, it never co-occur in our representation, so we wouldn't be able to calculate a probability for this sequence right here. On the other hand, if we have something like 1 and 2, they pretty much co-occur a lot, so I know that, okay, every time, not every time, but at least in this corpus here, if I have 1, it will be mostly connected to 2, and so on. So how do we calculate the probability using the formula that we just learned? So in this case right here, we look at the co-occurrence of the word that we're trying to predict and its immediate words. So in this case right here, I eat. It's I eat, yes, it's I eat. And then if the co-occurrence of those two right here, I eat, and as we saw before, it's 9. And then we divided this by the amount of words that we have on our previous context, which in this case is I right here. And with that, we can pretty much calculate the probability of a given sentence. In this case, if I have, I want English food, most likely we will, oops, I forgot to put the numbers, but most likely, okay, we have just the final one here. If we have this sequence right here, we can see that it's not very useful for us because most likely when we have this sequence right here, this is putting the probability down a lot for us, all right? On the other hand, depending on, let's say, what you're looking behind and we talk about our previous states, we can take a look on other embedded knowledge. This one here we already talked about, so what is the probability of 2 given that I have 1? But in this case right here, we see that for this vocabulary, it's most likely for us to have Chinese given that I have 1. In this case, we're talking about the food. Also, in this sequence right here, we can pretty much see that if we have this initial token right here, we're talking about the initial, the beginning of our sentence, and so on. Okay? Okay, so some practical things that we should keep in mind. Right now, we are multiplying all these probabilities, but we do everything in log space, as I said before, to avoid some underflows. Also, adding is way faster than multiplying. And also, later on, we'll revisit more about this log scheme here when we talk about neural language models as well. All right, and of course, log, they have some neat properties. If you're multiplying all these terms right here, you can just split them up. This will help us a lot when we talk about, when we start deriving in the next lecture, I guess, or lecture 5. Okay? Yeah, some language model toolkits, and keep that in mind, that's all prior to neural models, neural language modeling, right? Just this here, I think, is not available anymore. Okay, I'll revisit this. In any case, you can use either the Speech Technology and Research Laboratory. They have a nice speech language model. The natural language toolkit is pretty neat also. Most of this approach that we're talking, like calculate the term frequency, verse document frequency, a language model of a specific idiom, stop words list, all of this, it's kind of already done. So you can find this ready, so you just have to apply it, right? So, talking a bit about evaluation, okay? We're talking about how good or how probable a sequence is, but how do we know if things are good or the sequence makes sense or not? How do we do this? One way of doing this, we see how much our model makes sense. As simple as this. If your model generates some gibberish, it's most likely not a good model. If it generates a sentence that makes sense, it is a good representation or it is a good language model. So if we have probabilities for words that we know already they should occur in that sequence, if it's high, it's a good one, and it will make a sentence that it makes sense. If not, it will be generate some trash, then it's probably not a very good model. And you might ask, okay, is this a good way of evaluating your model? Yes, especially when you're talking about more specific tasks. Let's say you have a language model A, a language model B, and then every time you test your model, if you consider the end task, this is quite costly for you to do. So what do? You take a look on an intrinsic task, and I think we'll mention this later on, which is a way for you to probe your model if it's already good enough. There are some non-data sets like Wikitext. So if your model is able to predict this sequence of words good enough, then you move this to a more complex task. If your model is not even able to, let's say, generate words that are easy or none in that sequence, it's not even worth to bring this to the other task, all right? Of course, this is a proxy task, but we'll talk about this later on. So yes, of course, we train the parameters of our models. Right now, we're just talking about this probability, but later on, we'll see that we can kind of also apply some weighting schemes on this. So we train these parameters in our training set, and we test the performance in this model on data that, of course, we never seen it. And it might seem pretty obvious, like, yeah, you should not test something in data that you have already seen it, and you might think that this doesn't occur. Yes, it does. Have you ever read the paper from GPT, I think it was 3 or 2, I don't remember, the technical report from 3.5? They had a lot of problem with duplication of data, contamination of data. So even though it seems quite obvious, when you expand this to corpus such as the internet, how you can guarantee that you're testing a model on a specific task, and this, by whatever means, was not included already when you were doing the training. And this happens a lot, so it's pretty important to keep that in mind. Yeah, so we cannot allow test sentence into the training set, and this is pretty much one of the first things you should keep in mind, of course, and this is not only valid for our NLP class. On any machine learning course or any machine learning problem, you should keep that in mind. Yes, it sounds easy to say if you have a very clear training, testing, handout, and life is beautiful. It doesn't happen. So it will happen if you have well-established data sets. In the wild, unfortunately, that's not the case. There are some ways for you to cope with that. But before we get into this, how this training and testing setup work for us. So usually on an ideal scenario, you have an entire portion of your data here, and it's already splitted. So it's already curated in a way that you have training set and tests. In your test, it is somehow related with your training. It's not the same, of course, but it's there. On top of that, also sometimes you have this held out data. In our case, we have also called this developed set in our project. If you don't have this as a separate one, usually use a portion of your training set to do this, in which you use this part right here to adjust any free parameters that you might have, okay? And what happens when you don't have this really nice division? Well, you can split in 8-20, like 80 training and 20 testing, 70-30, or whatever other division that you have. You have to keep in mind some of the biases and problems that this comes along. Let's say if you have a random split, you should be able to guarantee that one specific class or one specific feature is not overrepresented in your training and it never occurs in your tests. So to cope with that, you can do like stratify sampling with or without replacement. You have to do, usually, you do a data exploration analysis in your data, and then you see, okay, if you're dealing with named entity recognition, you take a look on how many entities or locations or organizations they occur in your data set, and you make sure that they are somehow all distributed in whatever training sample you have. This is not trivial to do, by the way. Yes?
It sounds really quote-unquote easy in case you're dealing with some basic tasks like classification. But what about something like text generation? The training test set in this case. I mean, from the raw data, you have a text, for example, a book. You are trying to make sentences in the spirit of the author, for example. What would be the approach for the training test distribution in that case?
So there are a couple of them. All in all, it depends a lot on the task that you're trying to deal with. Let's say if you're doing text generation, if you're doing for a specific author or literature or etc., you will guarantee that this is represented as much as you can. If you're going to a more generic problem, such as free text generation, what modern approaches they do, on their training phase, they try to collect a diverse set of data in order to represent language in a better way. For example, they use Wikipedia, book corpus, news, and so on. And this percentage, this set of data to train on, they're not written in stone. So it's not like, oh, 20% here, 30% there. It's really, really varied. Some models, they're training 100% on books. Some models, they have a mix. There is a recent paper called Survey on Large Language Models, in which they probe the most recent approaches, in which they see, okay, what is the composition, the training composition of all of them, and you see that some really cool models, you would think that they would have a lot of variety in their data. No, they're 100% Wikipedia. On the other hand, you see that a model that generates code, which is also text, it does not use just code. It also uses free text, and the model gets better. So in this case, I would say it really depends what is the final task. If you're trying to represent a literature period, I will try to get as many elements or as many records as I can for that specific period, and hopefully try not to have one author overrepresenting all the others. That's at least one initial approach. But is this a guarantee that it would work? No.
About the overlapping of text, I mean, if you create corpus of different sentences, for example, you would have some familiar, for example, like a sentence is paraphrased version of another one. You get one in train and one in test. How do you come to that?
Paraphrase is a bit harder to deal with it. What happens usually is a deduplication phase. When you have large amount of data, usually you start a curating part of this, in which you will remove data that's duplicated. You have, let's say, exact same sentence, or according to whatever metric you're using, you might remove them. This is in theory. In practice, very few people take care of this.
So it's just...
It duplicates and it contaminates, okay? However, also, if you don't have any way of doing the splits, either because your data set is not that large, or you don't have enough meaningful examples, what people usually do, they do a k-fold cross-validation, in which you take the entire data set that you have, you break it down in whatever k-fold that you have, and then you train, let's say, in 9 parts, and then you test in 1. What usually also happens is some data sets, they provide on top of this training, which it might be small, a specific test set, but this is, in my opinion, even rare. And then what happens is, if you don't have this division, you use the entire data set divided in splits of train and test, and you keep moving your tests all over this entire split, and then in the end you report the standard deviation or the average, independent how you do this. Okay. Okay, I just see that I'm running out of time. Okay, evaluation of our models. So, ideally, you would test your model in a final task, but this can be extremely costly to do, either because you have large amount of data or you have a bunch of different tasks. Sometimes some task collections, if you look, there is a benchmark, it's called the Big benchmark. I think they have more than 100 tasks. So if you have a specific approach and you have to test every single alteration that you have on whatever model variations in this final task is extremely costly. If you start involving humans, that's even more costly because you have to pay, usually you pay or you do some sort of retribution to people that help you in your tasks. So what we do, we use some kind of proxy tasks. In any case, the best way to evaluate of your model, of course, you compare, let's say in our universe right here, we have two Enneagram models, and then you put them in the final tasks, such as spelling corrector, machine translation systems, and so on, and the one that does the best is the best one, right? Right?
Nope.
Why not?
Proxy task isn't representative.
Let's say this is the final task. It's always the model that does better, the better model. Yes? Mm-hmm. Exactly. And this actually is one of the discussions happening right now. How much, how much is, let's say, you're willing to pay and sacrifice for, I don't know, 2%, 1%, 0.5%? Not always, and this also reflects in our project, of course, not always the model that does the best is the best, simply because it's a very controlled environment. It might be overfitting to this scenario. Let's say you use, as you said, a bunch of resources to do this, and just keep that in mind, right? Especially if you're starting to write papers. There's a very common mistake like, yes, I have my approach, I test and compare with 10 people, and I'm 1% better. So my paper will be published, right? Not necessarily. So take care with this kind of mindset. All right. As we were saying before, it's hard to do this kind of extrinsic evaluation. Sometimes we rely on intrinsic evaluation, not only to start testing our models, but to filter things out. Let's say you have a model with, I don't know, being really naive, let's say 5 different versions of this model. One includes feature A, the other one you remove those features, or you have an extra layer in your neural net and so on. So you don't know which one you take forward to make your, let's say, your to-go model. So what we do, we test those things, we filter all those things into intrinsic evaluation tasks. And perplexity is one of them. We'll talk about this in a minute, which is pretty much what is the degree of surprise that we have when we are predicting a given sequence. There are specific data sets to do this. When I say specifics, like most people use this in the literature, Wikitext, there's Wiki 8, I think, if I'm not wrong. There are some data sets that they use this to already say, hey, this model or this, we had so many different selections and we went with this here. Is this perfect? Of course not. It can be a bad approximation, of course. Also, there is no guarantee 100% that if your model does well in this proxy or in perplexity, it will do well in the end task. It is a nice indicative though. Okay, yeah.
Is it really like a good idea to test your model in tasks that you as a human think that it should be well in? I mean, in case we're talking about text classification and we are taking the word analogies, for example, as a proxy task. I mean, I don't really care if that black box is doing well in word analogies. I only care about the classification task.
Mm-hmm.
And it's really a good idea to test it on a task that I, as a person, suppose that another person should be good at, in case we're talking about classification test.
People
I hope
do.
that makes sense.
I think I understood. What usually happens is, depending on the task that you're dealing, it's also a good intrinsic evaluation to see if the output makes sense. For example, let's say you're doing with word analysis or word similarity or even a text classification. It correlates documents that belong together. Yes, if you are, let's say, I don't want to say you're good enough to be an expert to see, okay, this correlation or this classification makes sense or not. If you know the task and you can evaluate this, it's a good way. Keep in mind, this will be cherry picking. Yes, it is a proxy. Sometimes we do this in paraphrase detection. If you know the language, yes, you can see, okay, this paraphrase here makes sense. But if you want to explore something that you're not that familiar, it gets harder and harder to do this. But yeah, people do this. Okay. Yes, evaluation. How can we predict the next word? There is the Shannon game, which is pretty much we give a specific sentence in which we already know in this specific sentence right here how well the next word will be predicted. So let's say if we have always, in this sentence here, I always order pizza with cheese and, if your model somehow predict one of the words that it should make sense, like mushrooms, pepperoni, and so on, we can say, okay, this is somehow a model is doing good in this task. If it predicts something like, I always order pizza with cheese and fried rice, which has a really, really low probability, most likely your model was not that good calculator, right? The problem is, usually in this game right here, we're dealing with unigrams. So we have the probability of every single word right here. And this is actually not a good idea. Why? We already talked about this, because simply words, they relate one to another. And this game does not show this for us. Okay, on the other hand though, this is really fast to calculate and to probe. Yeah, just some other examples. So we talk about perplexity and how we can use this to measure if one model is good or not. I'll turn the heat off because it's extremely warm here now. In any case, so what is perplexity? It is a measurement of how well a probability model predicts a sample. So it's pretty much related with the degree of surprise that we have on all the possible, let's say, variations or combinations that we have, how surprised our model is for that. So the lower the perplexity, the better it is, because you're not predicting something that's unexpected. If your perplexity is really high, it means that you have too many possibilities and you might be hallucinating in this case. Okay? So the best language model is the one that best predicts an unseen test set, of course, given a specific sentence. Another way, or a way to look at perplexity, is pretty much the inverse probability of the test set normalized by the number of words. So, and I think I included this here. Yes, so what is the perplexity of our model? Pretty much we just calculate 1 over the probability of that specific number of words that we're dealing with. So when we say we want to minimize the surprise of our model, or we want to have a lower perplexity, a lower degree of surprise, we're talking about maximizing the probability. And it kind of makes sense, right? Let's say if your model doesn't predict things that well, it means that it will have many probabilities that doesn't make sense, so the perplexity will grow. And if it's low, it means that it's not that crazy and predict things that do not exist, and then we'll have a low value. If we extrapolate this to what we just learned, for example, remember when we were talking about the sequence of words, and the larger it gets, the harder it gets to predict, because the recurrence of that specific sequence gets harder. So going this direction, let's say the more sequence that you have, the less surprise you're going to have, theoretically, right? Do you all agree with this? not much, but we'll get there. Okay, so how we do this? Again, we don't have to calculate the probability with all the words that we have. We look just a little bit behind. So we have here, we apply the chain rule again, but of course, we don't want to look to the entire distribution of words that we have. We look, in this case, in the bigram model, we look just a little bit behind. Okay, I don't know why the other thing is not here. Okay, I hope this is still recording, so we're going to look here now. So perplexity is a branch factor, so it's pretty much the weighted average of a branching factor. So the branch factor of a language is the number of possible next words that can follow any other words. So the more possibilities you have, pretty much the higher this value will get, right? Suppose we have a sequence consisting of random digits from 0 to 9. So what is the probability, or in this case, sorry, the perplexity of a sentence according to that model in which we have the probability equals to 1/10 for every single digit, right? In this case right here, we know that if the probability for every digit is exactly the same, the perplexity is 10, simply because on every single digit that we have, that will be the amount of different options that I have in this specific context. Okay? So in this case, imagine if we have, suppose that 0 occurs 10 times as often as integers in that same sequence that we had, what would be the perplexity in, oh, I already showed, sorry. In this case, the perplexity is going down, which means that the degree of surprise, the number of possibility is going down. And this makes sense because if 0 is occurring 10 times more than any other digits, the degree of surprise, or let's say the measurement of surprise that we have, is going down simply because one of those in that sequence, the probability is getting higher and higher with time. And if we extrapolate this into, let's say, our example with words, we can say that the more context that you consider, or the larger the number of anagrams that you consider, the surprise in that model will go down. It means that the probability of that specific sequence will go up. So in this case, if I'm continuous sentence, the larger the sequence gets, it's most likely that you will know what is the next word is going to be. The shorter it is, the larger is the search space that you're going to have for all the possible words that you have in a sequence. So this is one of the reasons why we measure if a model is good or not, at least in the beginning, looking to perplexity, all right? And just to show a visualization how this would look like, we pretty much talked about this already. Where is it? Yeah, so in this case right here, if we consider, let's say, the restaurant corpus that we had before, the beginning of the sentence starts with S and then I, and what is the most, let's say, probable word that we would have after I is 1, and the longer our sequence will get right here, the less options we'll have to follow through here. Therefore, the sequence is most likely to occur than, let's say, I want to eat North American food or something like this. Of course, this is highly dependent on the corpus. You do not expect to, let's say, train a specific corpus and use, and hopefully that will do well in, let's say, I don't know, sentiment analysis, in theory, but we'll get there. Shakespeare corpus, and I hope to finish this soon. So on Shakespeare corpus, if we take a look on all the tokens that we have there, we see that we have that Shakespeare produced around 300,000 bigram types of all the tokens available that we have. So it means that all 99.96% of all the possible bigrams were never seen, even though that they were still present in whatever corpus that we had before. So they never occurred there. And what it means for us that you can use this combination of bigrams, trigrams, and so on to simply mimic a text from an author, even though that author never wrote that. And this happens not only with more recent models, this already was happening long ago in statistical language model. And just to prove my point, do you have any idea about this here, who wrote this text, or where this text is from? Any clue?
The last one might be like Shakespeare or whatever.
That's a good guess. So all of them are trigrams based on Pride and Prejudice, the Wall Street Journal, and Shakespeare. None of them are real text. They're simply probability distribution. So before people get hyped with ChatGPT and so on, this was already happening a long time ago, right? So this is just another example. If you use Shakespeare text to generate, and I keep looking there, Shakespeare text, you will find that it will make a lot of sense simply because it is Shakespeare. It's not it sounds like, it is. It's using the same vocabulary from that author and possible bigrams and trigrams of that. So it looks like a duck because it is a duck in this case. So the first one here is using a unigram model, the second one bigram, trigram, and a fourgram. And it's surprisingly good how it sounds. All right. We mentioned this a couple of times already. The Wall Street Journal is not Shakespeare simply because depending on the task that you're using, you cannot use that corpus to represent something that does not correlate. And we'll see that especially around 2013, 17, where this X2VEC models, they start to pop up. People thought this was a silver bullet for every single NLP task, and they would use those pre-trained models for their specific tasks, and it doesn't work that well, simply because at that time, those models, they were trained into news excerpts, and then they were using this for any sort of different tasks. And they figure out that, well, this model here, this language model is not as good as we thought. Or in that case was not a language model, but it's a one model. So anagrams, they only work well for a word prediction if the test corpus look like the training corpus. And in real life, it definitely does not occur of that, because you will most likely look at things in your test set that they were not trained on, meaning that whatever your language model was trained, let's say if you try to predict or if you try to fix a given sequence of words and one specific word never occurred in your corpus, you won't be able to calculate that probability. So how do we cope with that? There's a couple of different ways. Before we get into that, of course, what that means for us, it means that we'll have some sparse zeros and also divisions by zero, and that's the last thing we want. Just to give you a better representation of that, let's say in this case right here, we have a training set that's deny, the, and so on here. If our test set looks like this, deny the offer, if I try to calculate the probability of offer given deny the, we'll see that these things here, they never occur. So one of the ways to deal with this is to assign a standard and fixed probability for all out-of-word vocabularies. One other approach is to remove out-of-the-word vocabularies from your test set. So the problem is, if this occurs a lot, you might end up with an empty test or some stupid probabilities that don't make sense. Also, other approaches, they go in the direction that let's take probability from known things and redistribute on things that we do not know, and hopefully this will be a good proxy, okay? But all of this we'll talk about on the next lecture, the next part when we start talking about smoothing. So, last time we were talking about how we deal with, let's say, test samples that are not present in your training set, simply because they will result in some zeros in our matrix of representation between terms and documents, right? And what it means that none of the words or the terms that we have in our test, they are not from our training set. It means that we will assign probability as 0 for them, and this is definitely not interest for us, simply because we don't want divided by 0 when we are calculating the occurrences of that specific term in our matrix. And then, of course, why I always have a problem changing this. Okay. So the idea also, on top of that, we don't want to divide our probabilities by 0, is that this simply does not generalize. In a very small control environment, most likely all the examples, all the samples that you have from your test, they will somehow appear in your training set, and that's fine. But if you want to move to a more real scenario, that's not the case, and then there are some artifacts to cope with that. We'll see some of them on the note slides that I'll share later on, or maybe I already did that. I include a couple extra ones. We'll just go over the main ones for this class, all right? And one of the main ideas, or I would say most of them, they try to regulate the probabilities of things that do not occur in our, let's say, in our data, in our corpus, by using the, let's say, the amounts or the probabilities of existing things. So you see that all this, let's say, techniques, they pretty much do the same thing. Either they extract from someone and put from someone that exists and put someone that does not exist, or we do some hard absolute discounting, or we simply normalize everything, or we add one, and all of them, they have pretty much the same idea, which is getting rid of these probabilities right here that are none for us. So imagine that we have a probability of these words happening right here, given this context, and we want to make sure that we don't have a bunch of zeros that will completely screw our language model. So what we do, we take from this, let's say from this, let's say these words here, allegation, reports, claims, requests, and then we take this count right here and we distribute among all the others that we originally did not have any probability assigned. And by the time that we do this, of course, we have also to recalculate all the counts, because if you're redistributing either absolute counting or the probability, all the existing ones, they have to be recalculated, because now your corpus is simply different when it was in the beginning. Okay? And then, okay, a couple of ways how to do this. Add one estimation or Laplace smoothing, which is pretty much we are adding 1 to every single word that we have. It doesn't matter if we have a bunch of them or none of them, we simply add 1, and this by itself will already get rid of a bunch of zeros that we had before. So remember when we were calculating the probability of this bigram right here, a word given its context is the count of the co-occurrence of them by the count of our specific context that we have right here. Then now what we'll do is we're going to add 1 to this count, and here we're going to add 1 to every single word that we have in our vocabulary. So we pretty much add our entire vocabulary there. Surprising enough, this already takes you quite far. So it's quite interesting, and we'll see how this will change the example that we saw on the last lecture about the restaurant corpus, how by just adding 1 and then we recalculate all the probabilities, how this changes completely the landscape that we have of all the known words, right? Yeah, okay, this is more like a side note. I don't know if I mentioned this last class. Every time we're calculating probability of a given corpus, it means that this is true or is the best estimation from that corpus. It doesn't mean that applies for any other or is it true for any other, but it's your best estimate that you can have for For example, let's say we have a specific corpus and there's 1,000,000 words, and then the word bagel occurs 400 times. And if we calculate the maximum likelihood estimate here, we'll have that the probability of this to happen is 0.004. This, depending where you apply this in your language model, it might be a really bad estimate because simply the word never occurs there. However, if you're, let's say, considering a specific corpus, this is the best you can get. It doesn't mean that will work out on every single problem that you have, and you will see this happening in later techniques as well. Hopefully today we're already getting to word embeddings, and this is pretty much what happened in the early years on word embeddings. People would train generic corpus of a bunch of text, and they would apply in every single problem, and they discover, say, okay, this doesn't work that well. Why? Because that was true for that specific training or that specific corpus in which they were using to compute their language model, right? But this is just a side note. So if we revisit the restaurant corpus that we had there, I don't know if you remember, but we had a bunch of term-by-term matrix on the recurrence. So I occurs with I 5 times, I want 108 times, and etc. Now, the idea is for us to simply add 1 to all the words that we have there, and by that, we are already changing the sparsity of this matrix. We don't have all those, let's say, empty dimensions that we had before. We still have them, and this might be still troublesome to work, and we'll get this on the next lecture. But for now, this is the best we can do to get rid of those inconvenient zeros, all right? After we do this and we add 1 to every single element that we had before, and by the way, there are techniques in smoothing that they say that you don't need to add 1 to every single element that you have. You do this for a specific threshold. Let's say if the count is below a certain number, you add to that count. If it's not, you leave the way it is, or in this case, for higher numbers. In this case here, we are adding for everyone just to illustrate the scenario, okay? And then after we add 1 to every single element that we had in this co-occurrence matrix, we have to recalculate the probability of them simply because now we are considering more words in our vocabulary. So the probability that we had before when, in this case right here, I want was 828, and before it was not that, was 827. Now, with this new number, we have to recalculate all the probability that we have here. And then for our example to I and eat, now we don't have the co-occurrence of 9 anymore, it's 10. We have the count of I, and simply we are adding the entire vocabulary. I don't remember if I put the size of the entire vocabulary last lecture, but it is here. And this will give us a new estimate that we had before. So, and just to put this into comparison, of course, after we recalculate the probabilities, we also do the reconstitutive counts. We'll see a simpler example how this here is happening. But just to make a comparison show to you, if we consider no smoothing at all, we have the absolute counts for our corpus right here, assuming that's the entire data that we have. And now after adding 1 to every single, let's say, element that we have in this matrix, recalculate the probabilities, and then reconstituting the counts, we see that some of them get really different from the initial count. For example, I1 here went from 827 to 527. Other counts, since they are not that frequent in our corpus, they would not smooth as much as this here that happens for 1 and I. I went from 5 to 3.8. The ones from 0, they were normalized accordingly, and so on. This whole idea is simply for us to, given that we know that, okay, these elements, they do not exist here, let's try to normalize them and recalculate all the probabilities that we had before. And how do we use this, and how those features, they are somehow meaningful? you'd be surprised if you use this as input features for any machine learning algorithm, you'd see how this changes whatever classification or regression they're doing. There's a huge difference when you're using the absolute counts or when you smooth them or when you weight them. The accuracy or even, let's say, the separability that they have is way better calculated, right? And going in this direction, we're moving on and on from a more sparse representation to a more dense representation. And it's really cool how those things, they improve all those machine learning algorithms. And this is pretty much the basic idea when we start talking about dense word embeddings. On top of that, of course, they have less dimensions, less features, but we'll get there, okay? Okay, still about smoothing. Sometimes it helps to use less context. Okay, so when we use, let's say, we talk about how we can use bigram, co-occurrence, unigrams, trigrams, and so on and so forth. Should we always use them? Not necessarily. If you have a good evidence that you have a lot of trigrams in your corpus, you should use it. If you don't, you back off to bigrams. If you don't have unigrams, bigrams, you use unigrams, and also if you don't have unigrams, then you smooth them because you need to have some sort of probability. However, best than simply using these hard cuts for how much context you're going to use in your language model or whatever probability that you have to calculate, what people usually use, they use some free parameters. It's called interpolation, in which you condition that probability to a free parameter and you adjust that. Let's say you want to give more importance to a word that's part of a location or a person or a specific part of speech tag and so on. There's a couple of ways of doing this. Simple interpolation, you have an absolute number for lambda 1, 2, and 3, and then you multiply that for whatever context that you have that your calculated probability of your entire sequence. Or you condition this according to the context in which you regulate whatever lambda that you have here according to the context that you have. So depending on these words and how they change, you will adjust this value accordingly. Needless to say, these parameters right here, they have to sum up to 1. And a natural question following this is, how do we choose these parameters? How much do you adjust them? One way of doing this is to use the head-out value that the head-out portion of the data that we talked last class. So you would train whatever probability distribution that you have in your training set, and then you start playing with different values, or you do whatever grid search you have to do in those free parameters, and hopefully one of them will give you the best value for that parameter. All right? Still, do you think this solves our problem to dealing with every single thing that we have in our test set as 0 probabilities? Do you see another problem when you're, let's say, how do you keep adjusting all the recounts every time? Do you think that's effective? Can you think about another solution that you would deal with words that you don't know how much they occur or how often they will occur in any given test set? This is one of them, of course. Because it's quite troublesome, right, to keep recalculating everything over and over again. For this example, we have 10 by 10 words. It's trivial. But if you have 10,000, 100,000, a million, this is not that easy. So one approach to deal with this is simply every single unknown word, you put a specific probability there, and that's it. Or you see how many unknown words you have that, and then you redistribute this the same way. Or you categorize unknown words in different type of unknown words, or you simply delete them. You would be surprised how much this was used, especially around 2012, 2014, when they were playing a lot with dense word embeddings in the beginning. Simply, if a word does not occur in that vocabulary, you simply delete them, don't use, or put a known word, probability of 0.00 and whatever, and you move on. Of course, this has some drawbacks, right? Let's see. But I think we can move forward. Okay. Another technique that we can also use to deal with probabilities that we did not see in our training sets called good Turing. And what is the idea behind that? We want the probability of unseen objects not to be estimated as 0, the same thing as before with add 1, but it kind of provides a straightforward rule how to deal with that. So the idea is we're going to take probabilities that we saw at least once and use this to estimate for any new element that we might have. And then with that, we reconstitute all the counts and all the probabilities all over again. All those techniques, they use the same idea. So imagine that we have this, in this scenario, we have a bunch of fish here, so 10 carps, 3 cods, 2 tunas, trout, salmon, and an eel. And then if we ask, okay, what is the next, the probability of the next species to be tuna, it's straightforward because we have this in our training set, so it's 2 by 18 because we know everything here. Now, if we start asking, okay, and what if I have a new species that is not on my training test? How do I estimate this? On the very first, let's say, in the probability of good Turing, it will say to you, take everything that you saw once, and that's the probability. Is it a bit harsh? Yeah, maybe, but it's a way for us to cope with this. So we take everything that happened once, so in this case right here, n to the count of 1, and then we use these 3 elements that we have, trout, salmon, and eel, and then we have that the probability of a new species is 3 by 18. Now, let's say we continue doing this game, and now I say, what is the probability now of tuna again? Consider the entire corpus that I have. Well, now I have a new fish, which I put a probability quite high because I combine every single element that happened once. So I have to recalculate that. Before we recalculate that, we already have a good intuition that for sure it will be less than the original probability, simply because the new element right now has a higher one. And in practice, we'll have more elements in this, and the probability now is completely different than it was initially. Okay? And how we're doing this. When you're using good Turing, pretty much we take a look on what is the probability for the elements that we've seen just once over all the elements that we have, all the entire count that we have in our data set. And then the same way we did the reconstituted, that's quite a hard word, reconstituted counts in the last example, we'll do this here again, in which we consider the elements that happen one more than whatever C that I have over this NC, and then we add 1 to whatever count that we have. But it will be better if we see an example. Okay. Some notes on this. First of all, do we need to do the reconstituted counted for all the elements? Not really. This work is quite old, but it still works quite well if you just want to apply this technique in a way that you rework your counts only after a certain number of elements there. If this number is above 5, you don't do it, but if it's below that, you probably want to recalculate this. Later on, we'll see that how much also you can discount from existing elements in your data set instead of going through all this trouble of adding 1, consider the entire vocabulary, doing the probabilities again, doing the recounts again. There's a simple rule that you can apply a very hard discount, and it works really well. And they tested this, I think was, we'll see later, 22 million words vocabulary, and it worked quite well, but we'll get there. Another alternative, of course, you can always add 1 to smooth, or you can put everything in log space, but we're not dealing with this here right now. It's just an alternative. So let's get back to our example and see how this actually affects the number in the end. Let's see how much less the probability is from our first example, which was less than 2 by 18, right? So let's say we have our 18 fishes here again, and if we ask how likely is the new data or the probability of good Turing to be catfish or bass or any other fish that's not on our list right here, normally we would say this is a 0, But since we want to use the estimates of things that happen at least once in our data set, we know that this here is 3 by 18. Now, if I ask again, okay, then how likely is the new one to be ill, or any of those elements right here that only occurred once? How that affect the counts, the probabilities, and the reconstituted counts of our example? So how do I redo the count that we had here? So first of all, I know that the element here is ill, so it just happened once. So 1 plus 1, 2 here. By our formula, we know that we have to consider the number of times that a given C, in this case ill, happens. So N1 is 1 plus 1, 1 plus 1, 2. So we have to consider the number of times that an element that appeared twice happened. So in this case here, tuna, we have 2. And how many times our N, in this case, N ill will happen. So is 1 right here. And then when we recalculate the probability of that ill over again, we already did the recount for this, or how many times an element that appeared once happened. So is this N1 right here is the new recount that we just did, so 2/3 by 18, meaning that in the end, if we are applying good Turing for elements that we did not see, we'll see that if we have to recalculate the probability of the already existing elements that we have there, these probabilities will drop accordingly. And then you can apply this, of course, for this probability for every single element that you have here. Just remember to do the recount before, okay? Okay, then we can move on to other smoothing techniques. In the slide notes, I put more details on absolute discounting and also Knister-Neel. I'll briefly mention about them. So all of them, they pretty much work with the idea of let's use the counts or the probability of things that we saw once and propagate this over and over again. If I don't have the counts for things that happen once, what do? Use the counts that you have for twice, 3, 4, and so on and so forth. It doesn't mean it will get better, but at least you get this computed, okay? Good Turing, we just saw. A stupid backoff, it pretty much assign a weighting factor to whatever count that we have, and that's it. Only, of course, if that specific word and context, they do not exist in our vocabulary in this case. And they should have a normalizing factor here, but maybe I forgot to include. But in any case, this is not that relevant for us. On the absolute discounting, this is more interesting. Instead of simply do the math for the recount and also the probability distribution over and over again for every single element that you have there, this work from 91, they pretty much did this for large enough corpus, and they start to see some patterns in this. That if you consider a bigram, the count of specific bigrams, the more you have on these bigrams, you see that this count gets more and more constant. And then they saw that if you take whatever absolute count that you have, and then you subtract, in this case right here, 0.75, in the beginning, it doesn't normalize that well, but the more you get, so the higher is your bigram count here, you see that this discount of aroundish 75, it gets more and more true, all right? Then we have interpolation the same way we had an interpolation free parameter before with add-one smoothing. They also do this on absolute counting. And then on the Knister-Neel model, the idea is pretty much not to work with a probability of just a word in its context, but how likely is that a given sequence is entirely new. And they formalize this into a mathematical concept, but it's not that relevant to memorize this. we should probably mention one thing about absolute discounting. Do you see a problem with this thing here? How we calculate this absolute discounting with interpolation weight, more specifically on this term right here. I think last class we talked about how unigrams, they're not that useful, right? Simply because all the words or letters or etc. they are independent from one another. So if you have whatever weight condition to this unigram distribution, most likely is not the most useful thing you might have. So just to keep that in mind, okay? I think this is really cool just to go over it. Do we really need a perfect construction when we are providing a language? Not necessarily, right? I mean, it's possible to understand what's happening there, and also you can work on top of an imperfect output. So keep that in mind for later on when we talk about language modeling, neural language modeling more specifically. Although if we have this as an output, we'll say this is garbage. But you would be surprised how readable this still is, right? And that being said, we can close lecture 3 here, and I will stop the recording. So